Thank you. Welcome back once again to the last module of Module 3, Module 3.3, Collision Theory and Effects of Temperature on Reaction Rates. So we're going to look at exothermic and endothermic reactions, energy profile for reactions, the Arrhenius equation, transition state theory, and then we conclude. Collision theory and effect of temperature on reaction rates. As the temperature rises, the average speeds of the reacting species increase. Like I said, once the temperature increases, their kinetic energies will increase. Consequently, there are more collisions per second, and this results in increase in reaction rate. Remember we said that in module 3.1, that as temperature increases, the kinetic energy increases and collision increases, and reaction rate also increases. The increase in collision frequency seems to explain the increase in reaction rate as temperature rises, but does not explain how rapidly the rate increases. In fact, the rate of many reactions doubles for a temperature rise of only 10 K, that is 10 Kelvin. So you can see, once there is a difference in 10 Kelvin temperature rise, the rate of reaction doubles, and that's what we want to find out. We want to see if we can find a reason for that. Since it is clear that the simple collision theory cannot account adequately for the increase in reaction rate as temperature rises, how then are we to explain the molecular terms, the relatively large increase in reaction rate with temperature? That's what we're trying to find out. During a chemical reaction, bonds are broken first, and then bonds are formed, and energy is required to break bonds and start this process, whether the reaction is exothermic or endothermic. We'll see exothermic and endothermic reaction. Therefore, it is reasonable to assume that particles do not always react when they collide, since they may not have sufficient energy for the necessary bonds to be broken. So we're now looking at something separating collision and reaction. What this theory is now telling us is that, fine, there must be collision before reaction. But again, it is saying that while the temperature increases, the reactant molecule speed also increases as kinetic energy increases. So which means collision will also increase. But what it's saying now is that not all collisions will lead to reactions, because bonds must be broken before reactions can take place. So there must be something that will guide for us to know those collisions that are able to go into the reaction. So it means that a reaction occurs only as a result of those collisions between particles which have more than certain minimum amount of energy, known as activation energy. So this minimum amount of energy is known as activation energy, and it is only those reactant molecules that collide and have more than this activation energy that can go into reaction. Now, this is exothermic and endothermic reactions. You can see the reaction profile. Look at the reactants energy on the y-axis, reaction time on the x-axis. Look at where the reactants are above the products. I will see the activation energy is the EA. So the reactants must, surpass this activation energy. It's just like somebody who is climbing a hill. Depending on the steepness of the hill, it is only those who have the strength can climb that hill. For example, that hill behind the hostels, where students go for mountain climbing during the weekend, sightseeing. It is only those. In fact, all the students who go for that, most of them don't even get up to the top of the mountain. So the top of the mountain can be taken as the apex. At the top of there to the reactants is what you call the activation energy. So you see the reactants going into products. When the energy of the products are lower than the energy of the reactants, the delta H, the change in enthalpy of the reaction, will be negative. And when it is negative, we say it is exothermic reaction, that is, gives heat to the surroundings. Whereas the second diagram, look at the energy of the reactants is lower than the energy of the products. And we have endothermic reaction, that is absorption of heat from the surroundings. So if the activated energy is very large, only a small proportion of molecules have enough energy to react, so that reaction proceeds very slowly. But if, however, the activation energy is very small, most of the molecules will have sufficient energy to react, and the reaction will proceed very fast. Of course, the delta H gives us the enthalpy of the reaction. Now, this is energy profile using the collision theory, and this energy profile, you see number of particles with energy E and kinetic energy. So look at our kinetic activation energy here. So this place that is painted black is showing the molecules that have enough energy, more than this activated energy, that have gone into reaction. The histogram above shows how the energies of particles are distributed. Now the area beneath the curve is proportional to total number of molecules involved. The number of particles with energy greater than EA, you see place painted black, is proportional to the area shaded part of above EA. Hence, the fraction of particles with energy greater than EA is given by shaded area under curve over total area. That gives us our fraction. Now, it is this fraction we're talking about that Maxwell and Boltzmann used probability theory and kinetic theory of gases to calculate this number of molecules with energy greater than EA, and is given by E to the power minus EA over R(T). EA is already activation energy, R is a gas constant, and T is the temperature. So which means the reaction rate is proportional to this number, because remember that it is this number of molecules with energy greater than EA that will go into reaction. That is directly proportional to the reaction rate. And since reaction rate is also proportional to rate constant, we now say that K is proportional to E to power EA over R(T). So equation 3 will be K is equal to, removing this proportionality, we put a constant A, and this A is as a result of Arrhenius, and this equation 3 is our Arrhenius equation. And that A, the constant, can be regarded as the collision frequency and the orientation factor. So it guides the orientation of collision of the molecules. While E to power EA over R(T) represents the activation state factor. That is the number of molecules with energy more than EA. A is determined by total number of collisions per unit time and the orientation of molecules when they collide, whereas E to power E over R(T) is determined by the fraction of molecules with sufficient energy to react. Now, if we take natural log of equation 3, we will arrive at equation 4. Ln K is equal to ln A minus EA over R(T). And the graph of ln K against 1 over T will give a straight line with slope equal to minus EA over R, and the intercept will be equal to ln A. From there, we can get the activation energy and also get the collision frequency or orientation factor A. We can also plot log, where we'll still remember what I said before, that ln X is equal to 2.303 log X. So we can plot log X, that's log K, against 1 over T. And our intercept will be equal to minus EA over 2.303 R. And intercept will be equal to log A. Sorry, the slope will be equal to minus EA over 2.303 R. And intercept will be log A. Of course, R is a gas constant. And from there, we can calculate the activation energy. Now, transition state theory, we mentioned collision theory. Transition state and collision theory is saying about the same thing, except the approach. Chemical reactions involve making and breaking of chemical bonds by shifting electrons. Consider this exothermic reaction. So according to transition state theory, reactants pass through a short-lived high-energy intermediate. So what the transition state theory is saying is that first, these reactants will come together and form a transition state. Now, this transition state will be short-lived. It is this transition state that will eventually go into products or revert back into reactants. The same reaction profile. So the transition state will be located at the apex of that hill, at the apex of that activation energy we saw in the other slide. So it is through this transition state products can be formed, or if the energy is not sufficient, it will revert to reactant. So if A2, B2 do not possess necessary amount of energy above their ground state, when they collide, no reaction will occur. That's what we're saying. If they do not possess sufficient energy to climb the energy barrier to the transition state, the reaction can proceed to completion. If they do possess, the reaction will proceed to completion with the release of an amount of energy equal to the activation energy plus E. The reverse of such reaction requires a net absorption of energy. This time now becomes endothermic. The reaction is endothermic, and if energy is absorbed as heat, it will now be 2AB giving A2 plus B2. We've come to the end of Module 3 with this end of Module 3.3. We've looked at collision theory and effects of temperature and reaction rates. We've looked at exothermic and endothermic reaction in terms of giving out heat and absorption of heat respectively. We've looked at energy profile, which we're able to use to arrive at our Arrhenius equation, and then looked at the transition state theorem. So while you listen to these video lectures, you also look at the material, look at a textbook, and then do some comparison and write up where you don't understand anything, and ask your questions in a physical class. Thank you very much, and welcome to the next class.